Hi, good morning all. Welcome to my channel Vijay's Physics Sprint. So today we'll discuss about the electrostatic potential energy of electric dipole when it is placed in external electric field. So what is the electrostatic potential energy of electric dipole placed in external uniform electric field? So this is the uniform electric field intensity. Uniform electric field means the field intensity is same at all the points, having same magnitude in same direction. That is known as uniform electric field. So electric field intensity E bar has same magnitude and same direction at any point in a given field. That is called as uniform electric field. Now in the uniform electric field, now we are placing electric dipole, right, minus q and plus q. The distance between this dipole is taken as 2a. 2a is a distance between two charges. Now when you are placing this dipole, the force acting on plus q, it is F is equals to aq, and on minus q, F is equals to minus eq. Equal magnitudes of force but in opposite direction, so that the dipole is going to be rotated or deflected small angle. So this is the dipole position after acting torque on dipole. Equal and opposite forces in opposite direction. So torque developed on dipole. Due to the torque, the dipole is going to be right tilted or deflected a small angle theta. So how much of work done? The work done to rotate the dipole of angle d theta. The work done, the small work done to deflect the dipole angle of theta, that is dw, can put in as tau into d theta. But tau, what is the tau? The torque acting on the dipole. The torque acting on dipole is equals to P sin theta. What is P? P is electric dipole moment vector, which is equals to 2aq. The distance into charge, A is the electric field. So that work done can be written as dw equal to Pe sin theta d theta. Then the work done deflect or rotate from theta 1 to theta 2. How much of work done to rotate the dipole from theta 1 to theta 2 in the uniform field? So applying the integration on both sides, that is integration of dw equal to integration of theta 1 to theta 2, rotating from theta 1 to theta 2, sin theta and d theta. Integration of dw, which is nothing but w, p is constant. Integration of sin theta d theta, that is minus cos theta, theta 1 to theta 2, right? That is w equal to minus pe, substituting the limits, cos theta 2 minus cos theta 1, or w equal to, that is pe into cos theta 1 minus cos theta 2, and this is the work done is stored in the form of electrostatic potential energy indicated with u. U equal to Pe cos theta 1 minus cos theta 2. So this is the potential energy stored or the work done to rotate the dipole from theta 1 to theta 2, which is stored in the form of energy known as potential energy of dipole in the electric field. U equal to Pe cos theta 1 minus cos theta 2. Okay. Now see some special cases in potential energy. Some special cases. Case 1. Rotated from 90 to some certain angle. The initial position is placed already perpendicular to dipole, electric field intensity. Now rotated some certain angle. Then what is the potential energy? U equal to Pe cos 90 0 minus cos theta. Nothing but potential energy Pe cos theta. This is the energy stored, or also written as minus P bar dot E bar is a dot product of dipole moment vector and electric field intensity. If it is a cross product vector which is equals to tau, the torque acting on the dipole is a vector product of dipole moment as well as electric field intensity, and the dot product or the scalar product which is indicated to potential energy. Now case 2. Here u equal to cos theta. If theta is 0, theta is 0 means the dipole moment is parallel to electric field intensity. Both are parallel. Then what happened? That is u equal to minus Pe cos 0 value 1. So u equal to minus Pe. If it is perpendicular, right, theta which is equals to 90, nothing but P bar, electric dipole moment is perpendicular to electric field intensity, then cos 90 which is equal to 0, then u is equals to 0. And fourth point, if theta is equals to 180 degree, cos 180 minus 1, nothing but P bar is anti-parallel to E bar. The dipole moment is anti-parallel, opposite to the electric field intensity. It is minus 1, minus of minus plus, then u is equals to plus Pe. The dipole moment and electric field intensity, the product becomes positive, and it is 0 is minus Pe. This is minimum potential energy and this is maximum potential energy. Okay, and it is known as, so this is minimum potential energy. Then in this state the dipole is said to be unstable state. So it is a stable state when these parallel to each other, then the dipole is said to be in stable state, and it is anti-parallel, the potential energy is maximum. In this case the dipole is said to be unstable state. Stable condition, stable equilibrium, and that is unstable equilibrium, right? So this is the potential energy of electric dipole, right? So u equal to minus P dot E. U is the potential energy or work done. The work done written as dW. dW equal to minus P dot E bar. Work done nothing but force into displacement, which is minus P into E, and force becomes minus P dE by dr. So the force can be written as F is equals to minus P dE by dr. If it is uniform electric field, then E is constant, dE by dr is equals to 0, then force acting on dipole becomes 0 in the case of uniform electric field. Now based on that formula, now calculating what is the force acting between two dipoles. If these two dipoles are in same line or parallel to each other, then how the force is going to be changed. So the force, electrostatic force between electric dipoles, and these dipoles are parallel to each other. This is the first dipole P1, right? It's a P1, and dipole, second dipole is P2. Electric dipole direction always from minus charge to plus charge. This is the dipole direction. So you can imagine one dipole here, minus charge to plus charge is a P1 direction, and one more charge, minus Q2 plus Q is one more dipole direction, P1 as well as P2, and these two are in the same line. So these two are in same line. Then what is the electrostatic force between these two dipoles? So force expression, just now we calculated minus P dE by dr. Okay, so along the axial line, the electric dipole electric field intensity becomes 1 by 4 pi epsilon naught 2p by r cube. On axial line, simply 1 by 4 pi epsilon naught replaced with k is a constant, so k 2p by r cube. So substitute here, then we'll get the force right? So that is F is equals to minus P1 and D1 on the axial line. So this is E2 second dipole P2 d by dr of E2. So is nothing but 2 K P2 by R cube. So F is equals to minus P1, 2 K P2 is a constant, d by dr of R power minus 3, differentiation, that is F is equals to d by dr of R power minus 3, okay, minus P1, 2K P2, that is minus 3 R power minus 4, that is plus 6, okay, K P1 P2 by R power 4, K is nothing but 1 by 4 by epsilon naught, 1 by 4 by epsilon naught, 6 P1 P2 by R power 4. This is the force acting between two dipoles when parallel, when these two are in same line, and this force is positive, means attraction force, so it is indicated with minus. So F is equals to minus 1 by 4 by epsilon naught, 6 P1 P2 by R power 4. This is the force between two dipoles when these are along the same line, okay? Minus charge to plus charge, and second it is P2, same minus Q2 plus Q charge. So electric field intensity in this direction, dipole moment vector in this direction. So electric field is nothing but along the equatorial line. Along the equatorial line, the dipole intensity, the electric field intensity, which is equals to 1 by 4 pi epsilon naught P by R cube, taken as K as a constant. So E equal to Kp by R power 3, right? Now force, I am calculating force minus P1 and dE2 by R dr, substituting force P1 dr, E2 is nothing but Kp by R cube, then F is equals to minus P1, K is constant, of course this is P2, okay, and d by dr of R power 1 by R power 3 is nothing but minus 3 R power 4 multiplying, then force is equal to 3 K P1 P2 by R power 4. Now substituting K value 1 by 4 by epsilon naught 3 P1 P2 by R power 4. So this is the repulsion force, so that is a plus, we got the plus signs of repulsion force. When they are along the same line, attraction force, there 6 P1 P2 by R power 4, here 3 P1 P2 by R power 4. When these dipoles are parallel to each other, right, then the force of electrostatic force becomes 1 by 4 by epsilon naught 3 P1 P2 by R power 4. Okay, so if you have any doubts, make a question in comment box. So like, share, subscribe my channel. Thank you all. Have a great day.